Hey guys, I hope you like the videos. We're gonna do one today on, this is really basic fundamental physics, but have you ever heard somebody say that heat rises? Completely untrue. See, with gases, you have buoyancy. So if you add a lot of energy to something, the particles are gonna move around a lot, right? So that fluid can now be displaced, right? But heat itself travels from a warmer substance to a colder substance, absolute. Sure, you can use piping, you can use pressure, even gravity, okay, will change that to some degree. It'll change the flow rate of how heat moves, okay? So you can cheat thermodynamics with certain conditions, if you will. Okay, it's done with electricity. One of the easiest examples is in air conditioning, they have something called an expansion valve. And even if you don't have an expansion valve, you'll always have a capillary system. But basically, what they do is they'll take this fluid, this Freon, it has a really low boiling point. So if we're out here in the atmosphere under 14.7 psi at 80 degrees or whatever, this stuff is gonna boil like crazy. So they have to contain it because it has such a low boiling point. But they'll use electricity to force a compressor to turn this into a liquid, and the liquid will be subcooled. Okay, so it's not really taking on any heat, it's isolated. And what they'll do is they'll pump it through a capillary system where the pipe gets really tiny and it only lets a little bit of gas into the evaporator. But when it gets to the evaporator, the first thing the evaporator does is it gives it a lot of room. It changes from a capillary to a bigger pipe. And so just by giving that fluid that amount of new space, okay, to move around in, it will start to boil off. But you got convection, which you could think of as cheese melting. You've got conduction, which you could think of as if you had a hot frying pan and you were near it, you'd feel the heat, right? But if you touched it, it'll move into your body like electricity. So that's how, especially with solids, like you touch something hot that's solid, the heat moves into you at a faster rate, right? And then you have radiation, which you could think of as the human body produces some light. You can't see it unless you look on infrared, but anything that contains thermal heat is going to give off rays. So you got radiation, conduction, and convection. Those are the ways that heat moves. That does not change. Okay, you can get into things like if you have a lot of pressure, you could restrict flow. You know, you could hasten flow, you could restrict flow. So like one of the ways we'll do it, we'll cheat the system is, and here's the greatest proof there is. The people that say heat rises, what they're going by is when firemen go into a burning building, they'll go in and poke a hole in the ceiling and vent the room so that the heat's not trapped. But again, that's heat contained in gas, which is a fluid. So the fluid is going to displace. Okay, but one of the greatest examples of this is, think about the summertime when it's hot outside and you're inside the house and it's 65, 70 degrees. You turn that air conditioner off, right? Or open a window, heat is actually going to come in, isn't it? Right? Think about it. It's kind of a trip, right? To all the people that think heat rises, just think about the pure summertime and think, heat comes in the summer, so it's definitely not rising. But yeah, a lot of people will put comments like that and think that, like, you know, heat rises when, and we know that's not the case. Thermodynamics, the first law, second law, all that has been long established, you know. In terms of entropy and enthalpy and temperature, those are all a little bit different. Matter has an intrinsic value, okay? You know, how much worth is actually in the stuff itself. So entropy has a lot to do with mass, chaos in a system, the potential for chaos in a system. Okay, enthalpy would be a more of a measurement of overall heat content in terms of like if I wanted to size a store, like let's say a Dunkin' Donuts, and I wanted to put in a heating or cooling system, I have to think about, okay, well, I have a coffee machine here, I have an ice machine here that produces heat, I got a Coke refrigerator over here that produces heat, and then how many bodies are going to be in the room, right? Because those all put off heat. So you might want to size the system higher because you have a lot of extra enthalpy going on. But energy remains constant in an isolated system. We know this. This is long established in physics, and it's really basic. But yeah, space itself can actually cause stuff to boil. Like if particles are contained, either be it through gravity, piping, you're using electricity, using any form of containment, okay, that can be changed really, really easy just by modifying the system. But the fundamental laws of physics are always going to be the same. So your heat's always going to travel from a warmer to a colder, regardless. You'll never see something that's really hot suck the heat out of something cold. It's just not going to happen. It's not the direction of flow. There is one thing about this that kind of complicates it, and that would be time. Time and gravitational fields. Those are sort of one of the only places where you could see something a little different happening. Like one could argue that a speck or a chunk or a mass falling in from gravity to the planet is almost like heat coming together, right? Because you've got energy in a clump, and that's in a gravitational field, and now it's going to move in orbit. And we know orbit is just the speed of the flat or curved ground below you, and then your speed, and the two are coming together. And when you want gravity to work really, really good, what you do is you deaccelerate. The stiller you get, the more the field acts on you. So a lot of times when astronauts, people are in space, when they want to come down to ground, what they do is decelerate. Okay, they need to really put the brakes on, and they have a process for that. And then now they can slide in. I call it the speed of a falling fluid, but it's basically here on Earth, it's 9.8 meters squared. And when you get into bigger and bigger masses, you get higher accelerations. The sun produces a free fall to us on Earth. So everything in the manifold and the clump is all falling around the sun, and it misses it. It's called a geodesic, and it's basically just a straight path in a curved space is really all it is. And one just constantly misses the other. What you want to picture is two trains, one traveling forward and the other next to it on the tracks. And you just picture in your mind, if these tracks were laid out straight, we wouldn't violate the parallel postulate. We would stay in each other's lanes and just go about like no big deal. But if we're accelerating on a big turn, and you have a big mass and a smaller mass, or the space is curved, like when leaves will blow outside against a 45-degree wall where there's a joining of the wall, you draw a little circle where that right angle is, where the walls meet, and draw a little circle. That's a gravitational field, because F equals ma, right? You're going to have force, you have a vector, you have a flow going on. And now these leaves are going to whack into this wall, which is more massive, so they're going to lose their acceleration, and they're going to end up resting in the gravitational field, right? Well, as more leaves blow in, and now you have masses sitting there, those masses have now mathematical potential to stop other masses, and you can get this piling up effect. This is why you'll see dust in corners. This is why you'll see piles of leaves next to a building, and you scratch your head like, that's weird. Why do those collect right there? It's really a type of gravitation. It has to do with masses meeting one another and